So in this ICP, we are using K-means clustering. So first we import our dependencies. We are loading in a credit card usage data file, and an example of what K-means can do for us is to segment our users into groups so that we can target specific users based on their spending habits. So here's our data frame. We have balance, purchases, one-off purchases, installment purchases, so on and so on. We have a bunch of economic data here. So we can get info on the data frame, and we can see that we have about 17 columns with numeric data and one column with a string data, the customer ID. So we're going to go ahead and drop that column because customer ID doesn't tell us anything. We're also going to drop any null data. And now we can see that we have only numeric data. We have no null data left. So we can describe the data set here. And it's important to note that we have standard deviation of 2000 in this column and 0.2 in this column. That's a big range, and having those numbers so spread out is not optimal for K-means clustering because K-means is sensitive to outliers. So what we're going to do before we scale the data, we're just going to look at some correlation data, and this helps us just visualize some of the data we have. We can see some correlations, like purchases and one-off purchases are highly correlated. But to get our data into a standardized format, we're going to use a standard scaler. We're going to fit transform that on our data set and get a new shape. So we have 17 columns and about 8,500 rows. And again, we can describe that data frame. And here we can see for our standard deviation, every column has a standard deviation of 1. Which is what we want. And for every column, it'll also have a standard deviation of pretty close to 0. So you can see like -2 to the -18th. That's basically 0. Now we can do K-means clustering. So we're going to use a for loop to loop over and create many K-means objects and add the inertia score to a list. Then we can plot the inertia score on a graph like this, so we can see the elbow. In this ICP, we identified the elbow to be around 5 to 9 number of clusters. So right in this region right here where I'm circling the mouse. So just for an example, we can take 5 for the number of clusters, fit that on our scaled data. And here we can kind of visualize the buckets. So in the zero index cluster, we have about 4,000 data points. And in the first index cluster, we have 86. So there's a spread there. But we want to visualize those clusters so we can get a better idea of where they lay. So as I said before, we have 17 different columns. So we had our shape, our data frame shape. So we have 17 columns, but we can only visualize 2 or 3 of those as humans. So we're going to use principal component analysis to get our data into a, here's where our principal component analysis is. And we're going to get that into 2 columns that try to describe the most variance as they can. We're going to fit transform that. And now we can have a 2-dimensional space where we can visualize our clusters. So here, the different colors represent the different clusters, and the black dots represent the centroids. So we can do this for 5 clusters. We can do it for 6 clusters, 7, 8, and 9 clusters. And we decided in this ICP that we would use 9 clusters because it had a, that's where we identified on the elbow plot. Let's go back up to the elbow plot. We said that 9 lies right here. So we said that 9 was kind of in the region where the slope begins to drop off, and we would want to stop increasing the number of clusters. Um, the reason you don't want many clusters is because it could be hard for other algorithms down the line. It could increase your complexity if you have too many clusters. So there's a trade-off there of the inertia and the number of clusters. But we decided 9 was the optimal fit. And this is what this cluster arrangement looks like.